Okay, let's dive in. What happens if you actually fall into a black hole? It sounds like pure sci-fi, right?
Mm.
But it's a question that really pushes the boundaries of physics.
It really does. It takes us straight into some, well, truly mind-bending territory about the universe itself.
And we're talking about black holes, these objects where gravity is just so strong, light itself can't get out.
Exactly. Formed from the collapse of massive stars, usually.
So, on this deep dive from Cosmic Origins Revealed, we're imagining that journey right into one.
Mm. It's a trip into a place where space and time, they get twisted, stretched to the absolute limit. It's important, don't picture an empty hole.
Right.
It's a huge amount of matter crammed into a tiny, tiny space.
Like squashing stars into something incredibly small.
Precisely. You've got your stellar mass ones, maybe a few times the sun's mass, or even thousands scattered around. And then the big ones, supermassive black holes. Millions, even billions of times the sun's mass.
Like Sagittarius A in our own Milky Way.
That's the one at the center of most big galaxies.
So, not a void, but this super dense thing. Okay, if you were heading towards one in a spaceship, what's the first weird thing you'd see? Assuming you survived the approach, of course.
Well, if it's an active black hole, probably the accretion disk.
Accretion disk.
Yeah, think of this giant swirling vortex of gas and dust spiraling inwards. Gets pulled in so fast, heats up like crazy due to friction. Billions of degrees.
Billions, wow.
Oh, yeah. So it glows incredibly brightly, emitting all sorts of radiation, visible light, X-rays, you name it. A real cosmic light show.
So you're not heading into darkness initially, but towards this, like, blazing whirlpool.
Exactly. A violent, beautiful whirlpool.
And I guess that intense gravity must mess with the light itself, right?
Oh, absolutely. Gravity bends light. It acts like a huge lens, a gravitational lens.
So things would look weird.
Very weird. The accretion disk might look warped, distorted, like a funhouse mirror image. And even stranger, light from behind the black hole gets bent around it. So you can actually see stuff that's technically hidden, appearing as a ring of light.
You can see behind it. Okay, that's wild. Gravity playing tricks?
Cosmic tricks, yeah.
All right, so you're getting closer. The light show's intense. The funhouse mirror effect is happening.
Right.
What about the feeling of falling, the gravity pull?
Well, initially, it just feel like free fall. Accelerating faster and faster, kind of like astronauts in orbit, but the speed just keeps ramping up.
Okay.
But then, your experience depends hugely on the type of black hole. Is it a small, stellar mass one, or a supermassive giant?
Ah, right. Two types. Let's take the smaller ones first. What happens then?
Okay, brace yourself. There's a term for it. Spaghettification.
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 How can
Does not sound pleasant. Cosmic pasta.
Pretty much, yeah. It's because the gravity difference is so extreme over even a small distance. Imagine falling feet first. Your feet are closer, right? So the gravity pulling on your feet is way, way stronger than the pull on your head.
Okay, I see where this is going. Yeah, it stretches you like taffy, longer and thinner. And as you get closer, that stretching force becomes astronomical. It would literally tear you apart, atom by atom.
Atom by atom.
And this happens before you even reach the event horizon, the point of no return.
So for the little black holes, you're done for before you even get there, stretched into nothing.
Basically, yes. Incredibly inhospitable, even from a distance.
But you said the supermassive ones are different. How do they spare you the spaghetti treatment, initially at least?
Right. For a supermassive one, like our Sagittarius A, the event horizon is much, much bigger. So the change in gravity across your body as you approach is far more gradual. The tidal forces are weaker out there.
So you don't get stretched apart immediately.
Exactly. You could, theoretically, cross the event horizon completely intact.
Wow. Okay. And Sagittarius A, how big is that one again?
It's got the mass of about 4.3 million suns, but it's surprisingly compact. If you put it where our sun is, its main gravitational influence wouldn't even reach Mercury's orbit.
Huh. That's actually smaller than I pictured for that much mass.
It is. And luckily for us, it's 165 quadrillion miles away. So no danger of it sucking us in, something we often cover on Cosmic Origins Revealed.
Phew, good to know. Okay, so supermassive black hole. You cross the event horizon in one piece. What's that crossing like? Do you feel anything? A bump? A whoosh?
Well, that leads to another really weird thing. The difference between what you experience and what someone watching you from far away sees.
Ah, relativity playing games again.
You got it. From a distant observer's point of view, as you get closer to the event horizon, time for you appears to slow down.
Slow down.
Dramatically. Your watch would seem to tick slower and slower until Right at the horizon, it would look like it stopped completely.
So from the outside, I'd look frozen in time.
Frozen, yeah. And you'd also appear redder and dimmer as the light escaping from you loses energy fighting the gravity. Eventually, you just sort of fade away.
Fade away, frozen at the edge, never actually crossing.
From their perspective, yes,
Yeah.
you'd never quite make it across.
Okay, that's bizarre. But what about my perspective? The person falling in. What do I feel when I cross that line?
This is maybe the most surprising part. Right at the moment you cross the event horizon, you might not feel anything special at all.
Nothing, really.
Locally, right where you are, space-time could still feel pretty normal. No big jolt, no flashing lights necessarily.
So I just sail across.
Pretty much. You still see the stars outside. You could even see that distant spaceship watching you, although their clocks would now look like they're running incredibly fast from your point of view.
Okay, wow, so the boundary itself isn't necessarily dramatic for the person crossing it.
Not right at that instant.
Yeah.
But once you're across, everything changes.
How so?
You've crossed the point of no return. The escape velocity is now faster than light. Nothing gets back out. Space and time inside are warped so profoundly that all paths, no matter which way you try to go, inevitably lead towards the center. Singularity.
So it's not like you can just turn around or orbit inside.
Nope. Inside the event horizon, moving towards the singularity is as inevitable as moving forward in time is for us out here. Space itself flows inwards, dragging everything with it.
Wow. Okay, so you're inside. You cross smoothly, but now you're on a one-way trip to the center. What happens on that fall towards the singularity?
Well, even if you survived crossing the horizon of a supermassive black hole, the spaghettification eventually catches up with you.
Ah, so you don't escape it entirely.
No, as you get much, much closer to the center, the singularity, the gravitational difference, those tidal forces become overwhelmingly strong again, even across tiny distances. So eventually you will be stretched and torn apart, right down to your subatomic particles.
So ultimate disintegration is still the fate, regardless of the black hole size. It just happens later for the bigger one.
Exactly. The end point is the same messy end.
And that endpoint involves the singularity, this thing at the very center. What is that, according to our theories?
The singularity is, well, it's where our current physics breaks down. It's theoretically a point of infinite density. All the mass of the black hole, everything that's ever fallen in, crushed into a space with zero volume. Space-time curvature becomes infinite there.
Zero volume, infinite density. My brain hurts trying to picture that.
Right. It's where Einstein's theory of general relativity just stops making sense. You can almost think of it as the end of time itself for anything falling in.
The end of time. Okay, but wait. If everything gets crushed into this infinite point, what happens to the information about what fell in? You know, what made you, or what made that star a star? Does it just vanish?
Yeah, you've hit on the information paradox,
Hmm.
one of the biggest puzzles in modern physics.
Paradox. Why a paradox?
Because a fundamental principle in physics, especially in quantum mechanics, is that information should always be conserved. It can be scrambled, rearranged, but never truly destroyed.
Okay, information can't be deleted from the universe?
Right. But black holes, especially with this idea of everything ending at the singularity, seem to be doing exactly that, destroying information forever.
So the laws of physics were contradicting each other. Black holes versus information conservation.
That was the problem. It was a huge conceptual clash. And it led Stephen Hawking to a revolutionary idea.
Hawking radiation.
Exactly. Hawking realized that due to quantum effects right near the edge, near the event horizon, black holes aren't perfectly black. They should actually emit a very faint thermal radiation, a tiny glow.
So they're not completely inescapable. They radiate.
Incredibly slowly, yes. Especially the big ones. Interestingly, smaller black holes are actually predicted to be hotter and radiate away faster.
Huh. And does this Hawking radiation solve the information paradox? Does the information somehow get out with the radiation?
That's the hope. And where the theories get really cutting edge and, frankly, weird, one idea involves quantum entanglement. Maybe the outgoing radiation particles are subtly linked to particles that fell in, carrying the information out in a highly scrambled form.
Scrambled information leaking out over billions of years.
Potentially, yes. But there's no consensus yet. It's very much ongoing research. Another related mind-bending concept is the holographic principle.
Holographic principle. We touch on that sometimes here at Cosmic Origins Revealed. It sounds like sci-fi again.
It kind of does. The basic idea is maybe all the information about what's inside the black hole, that 3D volume, is somehow fully encoded on its 2D surface, the event horizon.
Like a hologram, a 3D image stored on a 2D surface.
Exactly like that.
Yeah.
The math hints at this possibility because a black hole's entropy, basically its information content, seems proportional to its surface area, not its volume,
Yeah.
which is unexpected.
So reality inside might be described by physics on the boundary. That's
Yeah.
deeply strange.
It suggests a profound connection between gravity and quantum information, and maybe even that our perception of dimensions is more complex than we think.
And all this complexity, yet black holes themselves are supposedly simple, right? The no-hair theorem.
Ah, yes. That's another fascinating aspect. Once a black hole settles down, the theorem says it's defined only by three things: its mass, its electric charge, which is usually near zero, and its angular momentum, its spin.
Mass, charge, spin. That's it.
What's it? All the other details about what collapsed to form it or what it ate, whether it was made of stars or spaceships or cosmic dust, that information seems to be lost from an outside perspective. As Wheeler said, black holes have no hair.
No messy details sticking out. But maybe that hair, that information, is hidden, encoded on the horizon somehow, like the holographic principle suggests.
That's one way physicists are trying to reconcile these ideas, yes. And speaking of spin, most real black holes probably are spinning.
Kerr black holes, right?
Right, rotating black holes. They drag space-time around with them in a region called the Ergosphere. You really can't stand still there. Space-time itself is swirling.
Whoa.
And they don't have a point singularity. The theory suggests they have a ringularity, a ring-shaped singularity.
A ring singularity. Okay, just when I thought it couldn't get weirder. This whole journey, even just talking about it here on Cosmic Origins Revealed, it's just mind-bending. Warped time, warped space, spaghettification, infinite density, paradoxes about information.
It really pushes the limits of our imagination and our physics.
And it really drives home how much we still don't know, doesn't it? What really happens at the singularity? How is information preserved?
Absolutely. Those are some of the biggest unanswered questions. We need a theory that unites gravity and quantum mechanics, a theory of quantum gravity, to truly understand the center of a black hole. And we're not quite there yet.
But these mysteries, these extreme environments, they're incredible tools, aren't they? Forcing us to rethink everything.
They are. Black holes are nature's ultimate laboratories for testing the fundamental laws of the universe. They challenge everything we think we know about space-time, gravity, and information.
They force us to ask deeper questions about cosmic origins, about reality itself. It's kind of awe-inspiring, even if it is terrifying to imagine falling into one.
Definitely awe-inspiring. It shows the universe is packed with wonders and mysteries far beyond our everyday experience.
Well, hopefully this deep dive gave everyone listening a sense of that wonder. If your curiosity about black holes is sparked, definitely keep exploring. There are amazing resources out there. And of course, keep tuning in to Cosmic Origins Revealed for more explorations of the universe's biggest questions.